In this video, we're going to look at how to find areas and distances. Now, areas. We have a buttload of formulas for area. We know the area of a circle is pi r squared. We know the area of a square with side x is x squared. We have rectangles. We have rhombuses. We have trapezoids. We have, as I said, formulas coming out the wazoo. But what if it's something that's irregular? What if it's something that you can't just break up into a few smaller things, like, say, this? I want to find the area of this leaf. Well, I can draw a box. And if this box is 4 inches by 4 inches, that means I have approximately a 16 square inch leaf. That's really a crappy estimate though, because I have all this empty space that's been overcounted. So what I'm going to do is try a smaller box. Let's try this one, which is 1 inch by 1 inch. I can cover my leaf. Again, not great. I missed some spots here, but I overcompensated over here. But it's a little bit better than the other one. And I get 13 square inches. Let's do one better. Let's go even smaller. This box is 0.25 inches squared. And let's see, I'll fill that up and slowly fill this thing up with a whole bunch of little boxes. Still not going to be able to hit everything. I'm still going to have some missing spots. But places where I overcompensate and undercompensate. It's not perfect, a little bit better though. This is 8.75 square inches. Well, we can go even smaller. Let's say we do this one. And these those little red boxes are 0.01 inches squared. How many of those little boxes do we have? So we start counting these and we realize that that's a pain in the ass. We're not going to count all those boxes. There's a lot of squares and it would be a better estimate. I'm sure we can find a better way though. In fact, as a bonus, if you can find the area of this leaf, a better approximation than I have, I'll give you bonus. The only thing is you have to tell me how you found it and what the answer is. We're going to assume in the original picture, way back on slide 2, that that box is 4 inches by 4 inches. So use that to adjust if you make a copy of these slides. So now let's get to math. Let's try to look at a math equation. I want to find the area under the curve. Well, again, I'm going to, instead of filling it up with boxes, I'm going to fill it up with rectangles. And I'm going to use the left side of the function to tell me how tall this equation is. Sorry, this rectangle is. So drawing my boxes. The left side is f of 0, f of 1/2, f of 1, f of 3/2. And the width of these things, I broke it up into 4 equal pieces. So the width of each of these is 1/2. So if I want to find the area, I'll have 1/2 f of 0, 1/2 f of 1/2 plus 1/2 f of blah, 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 etc. All that. Simplified, I get 25 over 4, which is 6.25. Now we do left and right sums a lot, so we're going to go ahead and refer to this as L4. L for left, 4 for how many boxes we used. So the left sum gives us 6.75. You can tell it's an overestimate because the function is decreasing, so all of our boxes are sticking above it. So this is an overestimate. Let's look at the right side. Right side of my box, I will have f of 1/2, f of 1, f of 3/2, and f of 2, which unfortunately is not there. There's nothing there. Again, my delta x just means a change in x. We have 1/2. So my right sum is 1/2 f of 1/2, blah, blah, blah. Crank it out because I know the function. I get 17/4, which simplifies to 4.25. I don't know if that's simpler. We're going to call this R4 because, again, it's the right sum, and there's 4 of them. So we've done the left and we've done the right. We can also do the center. Take the center of this, so that's a half, that's a fourth, 3/4, 5/4, 7/4. So those are my 4 heights. My delta x is the base of the rectangle. It's still 1/2. So I have 1/2 f of 1/4 plus 1/2 f of 3/4, etc. I ran it through the function 4 minus x squared. Got all these hideous 16ths. Simplified it 43/8. And that simplifies to 5.375. We're going to call this M4, M for midpoint, and 4 for 4 boxes. So we've done left, we've done right, we've done midpoint. Let's try to do trapezoids. This is a little bit better because it's the corner. So we have 4 trapezoids. Well, actually that one's a triangle, but picky. The area of these things, we will have the sum of the heights, the average of the heights times 1/2, because that's the base. the average of the height. So I've got f of 0, f of 1 half over 2, f of 1 half, f of 1 over 2, etc. Simplify all that stuff, I get 25/4, which is approximately 5.25. The actual answer is 5 1/3, which is 5.3333. So that's a pretty close estimate. Turns out, obviously, the more boxes you use, the better your estimate will be. And if it is integrable, it doesn't matter which method you use. If you take the limit and take tons of boxes, you'll get the same answer for any method. So let me get you to try one. Pause the video and see if you can find R6, L6, and M6 of this. So if we have 6, that means we've got 6 boxes. This length is 12, so that means my delta x is 2. You have to figure out the height, the left side, the right side, and the midpoint. I didn't give you the function value, so you're going to have to guesstimate what these heights are. But see if you can find the value of the left R6, L6, and M6. I will wait. No, I won't. So you should have gotten that the left is 83.2, the right is 67.2, and the midpoint is 76. If you're not sure how to do that, there's another video that goes through how to work those examples. Now let's look at this one. Let's go a little bit more from scratch. We have my function is x cubed plus 1, and I want to find the area above the x-axis over the interval from -1 to 1, and I want n to equal 4. Well, if n equals 4, let's see, 1, 2, 3, 4. So that means, again, my delta x is 1/2. That's the base of the triangle. So I can do the right sum and get those rectangles, the area of those rectangles. And everything's multiplied by 1/2, so I'm just going to go ahead and push it outside. So 1/2 times, this is f of -1, f of -1/2, f of 0, f of 1/2. Cranking that out, I get 1.5. I can do the right sum. I will get, again, 1/2 times everything, so I just left that there. Here is f of -1/2, f of 0, f of 1/2, f of 1. We get 2.5. If we do the midpoint, and we will get approximately, well, we will get 2. So those are the 3 estimates. I'm not going to bother with the trapezoid because that one's just kind of a pain in the ass and we don't really use it anyway. So we can estimate the area by breaking it up into smaller boxes. And when we do the definition of these things, let's don't foreshadow. So we can break this up into boxes to estimate the area under the curve. But what does it mean? What do the areas represent? Well, it depends on what your units are. I mean, if it's just a plain old function, we're just finding the area. But let's say you have the function is y equals f of x, and the units of the area, you're multiplying base times height for those squares, rectangles. So the units of the area are going to be the units of y times the units of x. Okay. So let's say I have cost D in dollars of producing a car as a function of how many cars you are producing. So the units would be dollar cars. Okay, sometimes it doesn't make sense, but that's what the units would be. I don't know what a dollar car is, so that's not going to help me interpret the real world. Let's do one a little bit more interesting or makes more sense. If you are mapping the velocity, and the velocity, which is miles per hour, is a function of time in hours since 8 a.m. Well, my units are going to be miles per hour times hour. So the hour cancels and it's miles. This will give you your total distance. That's kind of cool. The velocity in miles per hour you are driving is a function of time or minutes since 8 a.m. Okay, this is different because you've got miles per hour minutes. Minute miles per hour. Okay, that doesn't help me as much. But if we could somehow cancel something, there's 60 minutes to an hour, I can get rid of one of the units and it would come out to be miles. But the way it is right now, I'm going to have to change something, otherwise my units are really cattywampus. So that's what it would mean if you're finding the area under the curve. Sometimes it makes no sense, like dollar cars. Sometimes it's miles. It just depends on what your function is. So that's the area. Next video is going to be how to nail that number down a little bit more closely.